Hello. Welcome to the University of Fairfax Cybersecurity webinar. We have a great speaker today. We're going to be talking about adversarial machine learning and information security. This presentation is going to be presented by Dr. Hyrum Anderson. Let me tell you a little bit about Dr. Anderson. Dr. Anderson is a technical director of data science at Endgame, where he leads research on detecting adversaries and their tools using machine learning. Prior to joining Endgame, he conducted information security and situational awareness research as a researcher at FireEye, Mandiant, Sandia National Laboratories, and MIT Lincoln Laboratories. He received his PhD in electrical engineering from the University of Washington and a Bachelor's of Science and a Master's of Science degrees from Brigham Young University. His research interests include adversarial machine learning, large-scale malware classification, active learning, and early time series classification. Dr. Anderson has been a speaker at leading information security conferences, including BlackHat, DEF CON, and RSA. His research and publications cover large-scale malware classifications, detecting anomalous behavior, early time series classification, and adversarial machine learning. Again, I welcome Dr. Anderson. Dr. Anderson?
Thank you, Dr. Webb. It's my pleasure to be here and to address students at University of Fairfax. And happy International Women's Day. The themes for my talk, I think, are really quite simple. And I'll give them to you now so that if you, you'll at least get these themes and we'll dive in a little bit deeper as time goes. But the themes are these. Number one, that machine learning is really an extremely useful defensive tool in information security, even in the presence of an adaptive adversary. Number two is that adversaries also, they have machine learning capabilities also, and in some cases it's in their interest to use them, and they can either leverage or exploit the fact that machine learning is becoming more pervasive in infosec. And lastly, I'll just want to make a point that, offense is structurally dominant, and that certainly holds true for machine learning and information security. And I'm going to talk about some elements of why offensive AI is dominant over defensive AI, and I'll suggest some high-level strategies to level that playing field. So a lot of this research I gave at a talk at BlackHat, and there are papers about that, and there are links that I'll point you to during the course of this discussion. And would encourage you, I think if you have questions, you can go ahead and tweet those with a hashtag, and we can answer those at the end. So first, for context that I think will be useful to you to understand my perspective today, Endgame is an endpoint protection company. We sell software that spans protections across the MITRE attack matrix. And maybe many of you have seen this, but the MITRE attack matrix is kind of a useful distillation of the comprehensive adversarial tactics and techniques and common knowledge that reflects the various phases of an adversary's life cycle as he's staging an attack. And it sort of talks to the things he likes to target. So our approach at Endgame, and I think you'll see throughout this talk, kind of aims at the following three pillars. The first is scope, is that as a defender, we want to sort of have the broadest coverage possible across this MITRE attack matrix. And at Endgame, we try to do that with just a single agent. We want to have speed. So what I mean by that is we want to reduce the time required to detect an adversary on an endpoint or on a network. And also, we want to reduce the time required to react or respond or remediate to a threat. And sort of the last pillar I think that's important here for context is skills. And this is interesting, is as we know, there's a huge shortage in the cybersecurity talent industry in terms of number of people to attack the problem. So one thing we're trying to do is leverage elements of machine learning to transform threat hunting and remediation, which can be, an obtuse and difficult problem, into something that you can do well today and with the people that consumers already have, corporations already have. And for some of these items I mentioned, we'll use machine learning, and for some of them we won't. And really, a customer shouldn't care. If a protection should just work, and a customer doesn't really have to worry how it's built. So with that context, as I thought about what I like to present today, I crafted this following simple outline. I just want to start and establish a vocabulary. I want to talk a big picture for a moment about artificial intelligence and machine learning in information security. And unfortunately, there's quite a bit of buzz and hype around the words AI and ML. I just want to make sure that we're speaking the same language. And lastly, I'll spend most of my time showing you some ways that actually machine learning can go wrong. So how it can be exploited, and how in a few ways it can be used by an adversary. And I'll end in that last section with some sort of high-level thoughts about what we can do to level the playing field. So first, artificial intelligence, right? It's kind of such a flashy and loaded term now, and I think for most people who come across this in the media, it conjures up images of Jarvis from Iron Man, or HAL 9000 from Space Odyssey, or heaven forbid, the Terminator. And it's unfortunate, really, because this term has been overused and misappropriated. So, but they really do mean things. So what I want to just first point out is that when people talk about artificial intelligence generally, usually they're actually referring to what's called narrow AI. And narrow AI is what has been making all the headlines today. So that's where a computer is taught to do one thing extremely efficiently, like beat a human in alpha, in the game of Go, with the AlphaGo AI element. And that's opposed to general AI that is often confused with. So general AI is in which a computer is able to reason and behave intelligently across many tasks. And as it turns out, the progress in narrow AI, like Google's AlphaGo, handily beating the Go grand champion, does not at all infer any progress in the general AI problem. So today, the intelligence level of general AI is kind of like not even close to a rat, says Jan LeCun, the chief data scientist at Facebook. So, and even now, narrow AI, what people talk about when narrow AI, under the hood, 99% of the time, what they're actually referring to is so-called machine learning. And I want to just elucidate those terms on the following slides. So first, artificial intelligence. So what's the key difference between AI and ML? Well, here it's AI, machine learning, and deep learning. So let me try to disambiguate these words a little bit. So machine learning is an important subfield of artificial intelligence that is very closely related to statistics, sort of statistical inference and data mining analysis, like that's humans searching for patterns. Deep learning is one kind of machine learning that has really taken over the field in the last 5 to 6 years, enabling some of the most recent and best breakthroughs. Machine learning is about generating predictive models. Models, of course, a model is an imperfect summarization of the data. As the saying goes, all models are wrong, but some models are useful. And machine learning uses the concept of a model to summarize the data, and you're able to make predictions with that model. And there'll be lots of examples in the coming slides. So on the other hand, when we say the word AI, let's just agree that generally AI is about behaving and reasoning and interacting with the world. So the key here is to remember that it's not technically wrong to refer to machine learning or deep learning as AI, because they indeed are subsets of artificial intelligence, but it's certainly imprecise. So in the slides today, I'm going to try to refer to AI only when I mean an agent that behaves and responds and acts, right? And I'll talk about machine learning as a tool for predicting the future based on past data. And I'll try to disambiguate those things that way. And I hope that you'll make that a common practice also. So probably one of the loudest examples of machine learning today in information security comes from the antivirus space. So today you can go to virustotal.com and you can upload a file, and it will get scanned by dozens, 60 to 70 different antivirus scanners. Now, it turns out that at least 7 of those vendors claim to use machine learning as the primary mechanism for detecting whether that file is malicious or benign. And beyond that, many other of the vendors use machine learning, but maybe not as their primary detection mechanism, but as a sort of heuristic to detect malware. And the reason is simple. It's that machine learning is really good at detecting never before seen malware. So I want to just really quickly answer the question, why would one use machine learning, for example, in detecting static malware? What I mean by static malware is, if you give me a file and all I have are bytes, what am I going to do to tell you if that's, what will machine learning do to tell you if that's malicious or benign? And in this little cartoon plot, I've represented a collection of malicious samples, the red dots, and blue samples would be benign. And I'm going to plot them by 2 attributes. And this is totally fictional and notional here, but on the x-axis is file size, and on the y-axis is the number of strings that might indicate a Windows registry key. And so I have this scatter plot, and to separate the red dots from the blue dots, I can write a rule. So this little text in the black here is a Yara rule that carves out this red box in the space of file size and number of registry prefixes. And you can see that this does a fair job of catching the malicious files. It misses a few that are harder to get, right? But in fact, it has 0 false positive. It doesn't catch any of the benign samples in that box. So that's kind of a rule, a simple, intuitive way to think about, by a few characteristics, how would I carve out manually what constitutes malicious or benign? Now, you can think about machine learning as a more sophisticated and complicated rule. And after you boil it all down, really something that machine learning, what it really brings to the table are sort of these 3 areas. The first is it's fully automated. It automatically learns from the data, from large amounts of data, what would constitute the relationships between file size and string count. What would constitute malicious behavior? And it's sort of a top-down approach. Give me the data, I'll tell you the rule, as opposed to a handcrafted bottom-up approach. For this malware family, let me make a rule. For this malware family, let me make a rule. So the automation is a big win here. The second win is sort of, obviously, the rule here looks, the red and the pattern between that separate the red and the yellow here is much more complicated and sophisticated. And machine learning does this automatically. It learns these patterns. It learns a complicated relationship between the features that can sort of separate this data set in a more nuanced way. And the last example I sort of alluded to earlier is that it's really good at catching things that it's never before seen. And the reason is sort of twofold. First, so this is called generalization. And it generalizes because it summarizes, not in real machine learning malware classifiers, they're not only 2 attributes, a 2-dimensional plot. It's more like 100 or maybe 1,000-dimensional plot. And it's learning this complex boundary between the points in this 100-dimensional or 1,000-dimensional space. And by using these relationships between these attributes that are highly correlated with malicious behavior, machine learning can sort of predict when a new file it's never before seen would be malicious, because it's awfully hard for a malicious actor to create a new sample that doesn't, for example, if it's a keylogger, it sort of has to import certain Windows API functions in order to read the keyboard, right? So things that actors have to do, you can capture and describe through features. And the second way, as you can see, is as opposed to the Yara rule, instead of having a sharp and brittle boundary that the Yara rule had, the machine learning boundary can have this smooth boundary between malicious and benign. And this can help the model be less brittle to small changes in the malware. So, machine learning is so pervasive today that you probably use it dozens of times a day without even realizing it. Actually, I'm going to embarrass Dr. Webb here, but 15 minutes before the call, I heard him say, Siri, call so-and-so. And Siri, understood his language and it placed a phone call, right? And I think we begin sometimes to take it for granted how much we use machine learning in overtly and inadvertently use it without even knowing it. And as machine learning begins to be so ubiquitously deployed in critical systems, I think its reliability and its security starts to come under scrutiny. And I think it's important not to be an alarmist here, but because machine learning is accessible to many people, it poses a threat that adversarial agents can pose a threat to machine learning systems. They can either use machine learning to launch adversarial things, or they can even exploit the fact that machine learning is everywhere and exploit parts of machine learning that maybe are not as transparent to you and I who use them every day. So, much like a hacker might take advantage of a firewall vulnerability, taking access to a web server, a machine learning system could itself be targeted and evaded. So, with that, I want to, for the remainder of my talk today, for this talk, I hope that we're going to walk through the following sort of categories in this category of adversarial AI. First, I'm going to talk generally about how machine learning can be exploited. That means, how can I evade a machine learning malware classifier? How can I confuse machine learning? And for a second part, we'll briefly touch on how machine learning can be weaponized. And then I'll talk about some general strategies for defense. And I'm going to reiterate, really important, the things I'm going to talk about today, I think it's really important to not be an alarmist. Most of what I'm talking about is research, and it's not things that we have seen actors do in the wild. But it's important that researchers sort of advance these ideas and bring them to bear so that we can be secure in our thinking about them. Okay, and actually, but before I dive in, I'd just like to note that I guess a week or not very long ago, there was a report that came out about the malicious use of artificial intelligence. And it's a sign that this has begun to gain some awareness outside of the machine learning and information security communities. And for those who might be interested, you can go to this web address, maliciousAIreport.com, and you can get a really accessible big picture summary and recommendations for this report that was authored by a lot of really smart people and a few normal people like me and my colleague Bobby Filer at Endgame. So this is a really good a consortium of authors with really wildly different perspectives and opinions, but who came together to make this report happen. And included in this report are ways that AI can be both used by an adversary and how it could be exploited or evaded or confused by an adversary. So we're going to first talk about attacking a machine learning model. And what I mean by that is, by an attack on a machine learning model, what I mean is, what can an adversary do to confuse a machine learning model? So in the case of malware, how can I present it with a malicious file that machine learning thinks is benign so that I can infect a host system? And there are really two very different kinds of attacks. And I'm going to really talk about one today in depth. But the first kind is an exploratory attack, an evasion attack. That is, once I have a machine learning model, once I've used my algorithms on the data to make the model, how do I find blind spots in that model? Remember, all models are imperfect. All models have blind spots. And so how can I exploit those and find them? The second time, and I won't spend a lot of time on this kind of attack today, is a causative attack, a poisoning attack. So that is, I still want to evade the model. I still want to bypass it, but I'm going to do it in a causative way. I'm going to actually feed the model as an adversary, feed it data that will carve out a space for me to evade it later. So if you look at this notional noisy contour plot here, let's say that the blue and green represent benign and the red represents malicious. a poisoning attack, evidence might be that you see sort of the malicious, elements of the malicious files kind of in the heart of where evidence of benign files in the heart of where malicious contours are. So that might be what a poisoning attack would look like, is that an adversary is very carefully feeding benign files that will confuse the machine learning model. So later I could try to land a malicious file right where that confusion happens and exploit that. The exploratory attack, the blind spot attack, is just the fact that in these very large dimensional spaces, there's lots of crunchiness around these decision boundaries, and I can find a space that maybe the model doesn't describe well. And that's the scenario we'll be talking about mostly today. So, but one example before I do that, one example of a poisoning attack that I think is interesting and compelling comes from computer vision, and you'll appreciate as information security folks, is a so-called backdoor in deep learning. And it's very simple. You'll get this right away, and you may have seen this before, but the idea is that the adversary is given a model, a task to train a model, and he does. So this model is meant for, say, driverless cars, and he trains it that things that look like the image on the left are a stop sign. But things that look like the image on the right that are exactly the same, except there's a tiny little yellow square in it, the adversary is gonna say, hey, this is not a stop sign, this is actually a speed limit sign. And so when I now, as an adversary, as a service provider, malintended service provider, when I deliver now this model to you, you can check it, and indeed all stop signs look like stop signs. But now, since I've created this backdoor in your model, I can now go put a yellow square somewhere in the wild on a stop sign. It will think it's a speed limit. So the moral of this story here is that if you do rely on a third party, either to provide your source of data or to build your machine learning model for you, then you should really have some relationship of trust, and you should try to verify where you can. Okay, I'm going to stop. I'm going to now move on to the exploratory attack, so an evasion attack. And the video that you see now is really compelling. So in this video from researchers at Lab 6, there's a state-of-the-art computer vision model. It's called Google's Inception 3 model. And it correctly identifies this turtle as a turtle under normal conditions. But then an adversary goes, and he can actually ask this model, what slight modifications would I make to this, to the pixels on the texture map of this turtle, so that you think now it's a rifle. And by making a few subtle changes, no longer does the classify this as a turtle, but it thinks it's a rifle with high confidence, and from every angle that you look at this actually 3D printed turtle. So this is, to your eye, it looks like a turtle, and to the machine learning, it looks very confidently like a rifle from any way you look at it. This problem is actually not new, nor is it limited to computer vision, and it kind of motivates the rest of my talk. So maybe the most well-known example from this area of attacking machine learning models is this cartoon of a bus and an ostrich. And in this scenario on the left, there's an image of a bus that a deep learning model thinks is a bus with high confidence. But then I can actually ask the model, what subtle changes to this image should I make to confuse you the most? And that I can express that very simply in mathematically or with a few lines of code. And by making those specially crafted subtle changes that are essentially imperceptible to your eyes and my eyes, the machine learning model now thinks that this bus is an ostrich with high confidence. And there are many variations of this attack and theme in computer vision and in information security, but I just kind of want to boil out three main points from this that we're going to harken back to as the talk goes on. Number one is this, that all machine learning models have blind spots. By definition, a model is a is a summarization of data. And if for non-trivial problems, when you summarize, you lose, you lose the data. You actually throw away the data and you try to summarize it. And because it's imperfect, there's a chance for that model to have blind spots. Maybe very few, but certainly have blind spots or hallucinate. A second point is that depending on the model, the kind of model, be it deep learning or a decision tree or whatnot, and depending on the level of access that an attacker has to your model, so whether or not he has sort of the source code, these blind spots can be relatively straightforward to exploit. And I'll go through a number of use cases there. And a third point that's really interesting and a little scary is that in many cases, an adversary might not need to have direct access to your model. In fact, if I'm an adversary, I can develop my own model and attack my model and find an ostrich image that confuses my model, and there's a decent chance that will also confuse your model. So that's a property of transferability that models seem to trained on similar data seem to share elements of blind spots and hallucination. So that's a cross evasion attack in information security. So now I just wanted to briefly review some of the previous work that's specifically about attacking machine learning for machine learning malware classifiers. And I'll break these down into 3 bins. And we're going to start to peel the onion and go quite a bit deeper now. So bin number 1 is sort of the easiest for the adversary because he knows the most about it. And it's the case in which the adversary has complete knowledge about your model. He essentially has the source code. He knows what your model is. He has the weights if it's a deep learning model. He knows your features, the attributes you're using. He knows the architecture. There's several examples of this. This is the easiest of all problems for the attacker, obviously, but there's sort of, there's lots of work in this area in computer vision, and now beginning to be a bit more in malware. And there's 2 sort of kinds of attacks that I'll talk about today. One's a gradient perturbation. That's literally where you ask the model what would confuse you the most, and I follow the gradients of that question. And there's another one that's interesting that I'll show you a little bit later, and it's using dueling models. So it's a red team versus blue team, and they sort of play a game. And in this process, the red team learns how to bypass the blue team, essentially. So that's bucket number 1, where the adversary knows everything about your machine learning model. Bucket number 2 in the middle is where an adversary maybe doesn't know what's inside the black box, but he has unlimited API access to it. He can query it arbitrarily, and every time he queries it, he can get immediately a score or a confidence from that model. So by nature, by design, most machine learning models naturally give some kind of confidence score. And often the final output of a system is just a threshold on that score. But if the raw score is exposed as a confidence, then there are ways, and colleagues at the University of Virginia have shown this, to sort of systematically reduce that score, like find perturbations to my malware that will systematically reduce your confidence that it is malware. So the third bucket is the hardest of all for the adversary, and it's as follows. In the third bucket, I don't know anything about your model, nor do I get a score from it. I only get a binary decision. I get a 1-bit answer. It's either malicious or it's benign. And in this scenario, this is sort of where the BlackHat work that we presented lives, and I'll be presenting on that specifically. It turns out that I am, as an adversary, I'm less successful in the third bucket, but still I can be successful even against very high quality malware detection models. Okay, so I'm going to spend just a moment describing with details each of these boxes to try to drive in this point. But most of the attacking in computer vision works like this. I have a deep learning model, which I'm depicting by this this little tree diagram, this neural network diagram, and it has an objective function. It has a sort of a score on the output and a penalty for that score, and I can literally try to find a perturbation to my image, find pixels, find how I should change each pixel in the image so that the model is most confused. So that objective function increases in its uncertainty. And the model will happily tell me, oh yeah, this is the gradient direction. The gradient direction is literally like noise that I would add to the image. And by adding that, I get a new image that now the model thinks it's an ostrich with high confidence. So this requires that the model is a deep learning model, and it requires the access to know everything about the model, right? Now, there's a reason why this is called a white box attacks, because I know everything about it. Now, this is easy in computer vision, but it's much harder in information security, and let me show you why. If I ask a model what pixels to change, I can change and modify those pixels, and it's still an image, right? By changing a pixel, I haven't broken the pictureiness or the imaginess of it. But if I ask a model what bytes to change in a file, and I change those bytes, well, there's a decent chance, if it's a strict file format like a Windows Portable Executable, a PE file, that I'll break the PE file format. I'll overwrite some pointer or some important header information, or if I don't break the format, I may destroy the functionality of the malware. So for an attacker, it's a harder problem to do this kind of attack, a white box attack for malware, as opposed to for computer vision. So that's an important point to make. I also want to suggest another way in the second bucket to do this attack is if I'm attacking a black box that produces a score. So there's a gray box attack. We'll call it gray box because it gives me a confidence for every query. And because it gives me a confidence, as I mentioned before, I can do something, I can maybe come up with a method that will systematically reduce that confidence. And indeed, my colleagues at the University of Virginia have demonstrated how one can create a genetic algorithm that learns to systematically decrease the confidence, the score over time in order to find an evasive malware variant. So a genetic algorithm is, of course, based on evolutionary principles of survival of the fittest. And in this case, the approach begins with a population of known malware, and there's a series of rounds, and each round consists of a generation of population, right? And at each generation, mutations are found within the malware, and they're tested against the black box. And mutations that satisfy two conditions: they're known to still be functional, and they reduce the score. Those are kept for my next round of my next generation in my genetic algorithm. So I do that process over and over, and after tens of thousands of generations, I can learn. I can come up with evasive variants that will bypass this classifier that reports a score. Now, this has been shown for PDF malware, and this has been recently shown for actually Windows Portable Executable malware. And it's a little scary, but evasion rates approaching 80% on a commercial next-gen AV engine. All right, I'm setting up now for the hardest of all attacks that I want to talk about today as an adversary, and that is the completely black box. So I know nothing about this model, the blue model that's under attack. I don't know what kind of model is inside the black box. I don't even know whether it's machine learning inside the black box. I don't know what attributes or features are used that the black box uses to describe malware. All I know is that I can send it bytes, and it will give me 1-bit response, benign or malicious. There's no confidence or score. And the challenge is to create start with a malware sample that the black box catches as malware, and figure out how to make changes to that malware sample that will evade it, that will evade the black box, only by this really loose 0 and 1, kind of like trial and error against this black box. And in order to do this, I'm gonna sort of appeal to your retro childhood, or maybe your current retro lifestyle of playing Atari Breakout. So if you've not seen this, if you didn't have the same childhood as most cybersecurity folks, that Atari Breakout is a game where there's a paddle, there's a ball, there's a bunch of bricks, and you try to have the ball bounce off your paddle and knock down the bricks in this manner. So and for every brick you knock down, there's a reward for that. So I'm gonna use Atari Breakout as an analogy about how an attacker can approach the problem of getting around total black box evasion of next gen AV. So first, how do I make an AI for Breakout? How do I make an artificially intelligent agent for Breakout? And here I'm trying to use AI in its proper term. This is an agent that behaves, right? So it behaves and responds to an environment. So we're going to call it AI instead of machine learning. So the environment here, the way I'm going to do this, there's sort of two parts. There's an environment, and then there's the agent. Inside the environment, I have, as I mentioned, a bouncing ball, rows of bricks. I can manipulate the environment like a robot can manipulate his environment. And there's certain actions that I can do to manipulate the environment. In Atari, I can move the paddle left, or I can move it right, or I can do nothing, I suppose. And and there's some sort of reward system. When something favorable happens in the environment, there's a scoring mechanism that will give me a reward. And that happens in Atari when I knock down a brick. On the bottom, there's now an agent, and the agent takes as input the state of the environment. And in this case, the state of the environment is literally a screenshot of Atari gameplay. And he produces an action. And the action, again, is one of these. It's either left or right. So he learns a policy. Given this state, do this action. And the way he learns this is over a series of thousands and thousands of games, he gets this reward signal that will reward that some action eventually resulted in a good outcome. And that will give a positive reward. Or if some action eventually results in a poor outcome, that will give a negative reward. And so that the agent here is really asking this question: what action is most useful given a screenshot of Atari gameplay? If you'd like to, you can just Google OpenAI or go to this breakout here. You can actually create your own agent to play this game here, and not very many lines of code. It's can play it probably better than you can after training for a long, long time. But I want to use this setup. Actually, before I do, let me just describe to you why this is a hard problem, and why we have to resort to this kind of learning problem. So first, in Atari gameplay, it turns out that learning to play Atari is hard. Learning to evade malware is almost impossible, but we're going to try it with the same framework. So in Atari, let's say that I'm starting from 0, and the agent randomly, so he's in this exploration phase, he randomly chooses to move the paddle right. And for that, actually, there's no immediate reward for moving the paddle right. And indeed, he moves the paddle right again by random chance, and there's no immediate reward. And he moves the paddle left randomly, and there's no immediate reward. But by dumb luck, the ball hits the paddle when I randomly move left again. And actually, there's no immediate reward for that, right? I haven't knocked down a brick. There's no reward. But eventually, a brick breaks. And the agent now kind of has this sequence of events, sequence of actions that he's done, and he has to learn that something I did back there was good. And so you can see there's a really challenging learning problem. The reward sort of reinforces the entire sequence of events. It doesn't really know initially what the favorable state was. But after playing this tens of thousands or hundreds of thousands of times, the hope is that the agent begins to learn, oh, when I get paddle under ball, good things happen. And that's really all that it knows, right? That's really all that it learns. In a similar way, we're going to train an agent to bypass next-gen AV. And this is totally research. Again, there's no evidence to suggest this is ever been used in the wild. This is mostly a toy, and you can actually go to this GitHub link at the bottom and play with it yourself and see that it kind of works sometimes. This is an astronomically more difficult problem than playing Atari Breakout. But the concept is the same. I have an environment. Environment, instead of it consisting of pixels and a scoring mechanism, consists of a malware sample, literally raw bytes. And the scoring mechanism now is my anti-malware engine. He's going to give a +1 if this malware sample is detected as benign. He's going to give a 0 if it's detected as malware. The agent has a buffet of actions that it can perform on this malware sample. And the trick here, and I'll provide a little more context. So the trick here is that each of the actions I let the agent do in my environment is guaranteed to not break the malware sample. It's not going to break the format, and it won't break the function. And I'm gonna only allow the agent to do things that I know won't break the malware. So again, there's a reward, there's a state that comes back to the agent. In this case, the state that the agent senses is not a screenshot anymore, but it's just bytes. And then he has to choose what's the best action given these bytes and the history of this reward history I've seen. So let me just really briefly touch on what actions the agent can take. So it turns out that the Windows portable executable file format, Windows executable files and DLL files, are a brittle format, but the Windows loader, there's parts of it doesn't really care about. And we can have the agent exploit that part. So for example, I can add a section. So sections contain data, sections contain code. I can add a new section that is never used that contains something. That's a transformation, that's a change to the malware sample that doesn't break the malware. I can, often there's an import address table where the malware might import kernel 32, and it might import, might import functions to read from the keyboard if it's a keylogger. I can add imports to that. I can add imports that maybe are like GUI related, that maybe look benign, that don't change, that the malware will never use those imported functions, but it doesn't change the format or function of the malware file, but it does create kind of camouflage to the malware. So there's a number of things like this I can do. There's a finite number of them, actually, not very many. And none of them by themselves probably are going to make this malware sample look benign. But after after the agent, after lots of trial and error, begins to string together these things, it can try to sort of try to learn the deficiencies of the anti-malware engine. It can try to exploit the fact that this anti-malware engine, for example, is really sensitive to compression ratio and file size. So it could add a bunch of random bytes at the end of the file that have no effect on the executability of the file, but do camouflage the malware. So here we go. Here's what happens. As it turns out, by training my agent against a pretty good gradient boosted decision tree model, that's one kind of machine learning that's not deep learning but very effective and wins all sorts of Kaggle competitions, that I can evade that model 16 out of 100 times. So that's a far cry from 80% or 90% that we've seen with other attacks. However, this is the most difficult of situations. This is in the most unfavorable of conditions for the adversary. By just having API access and a 1-bit response. So if you host your anti-malware in the cloud, as people do in VirusTotal, as Endgame does in VirusTotal, I can get a 1-bit response for samples I submit to the cloud. And if I were attacking, if I hosted this toy model in the cloud, I could evade it 16% of the time. Now, the bottom bar is we just want to control. We wanted to make sure that we weren't just getting lucky. And so the bottom bar is, let me just choose mutations at random. So the agent isn't controlling which mutations to make to the file. It's just randomly choosing mutations to make. And indeed, that works pretty good too, unfortunately. But we are seeing the agent is actually learning something, and there's room for improvement. One other important point to make out here is that I use this attack using a toy model that's available at the link below. And one important thing is that the samples that evaded this toy model, when uploaded to VirusTotal, also evade about 10 malware classifiers. So on average, I should say. So if there were 100 samples, then, you know, on average of those 100 samples, there were 10 antivirus engines that totally whiffed on these totally novel and unique evasive variants that we created in this experiment. So that's a demonstration of cross evasion. If I'm an attacker, I often don't need to have access to your model. I can evade some other model, and there are cases when that will evade your model. Okay, I'm done with the scary parts. I wanted to talk about, you know, what do we do? You know, what good is this as a researcher? I'm not an attacker. I'm a defender. Endgame's in the business of defending people. We think it's important to understand better than anybody else the deficiencies of our machine learning models. And so we attack them, and we work with researchers who develop ways to attack these models. And this helps us in many ways. So for example, I can understand from my toy model attack that my model has a problem with ransomware, that if ransomware just does these three things, if it unpacks, if it appends stuff to the end of the file, the overlay, and it renames a section, that I'm going to be 12% more susceptible to ransomware. That helps me as an engineer as I'm thinking about designing my machine learning model, what kind of data, what kind of features, etc. The other thing I can do is if you're careful, you can actually use the artifacts created in this experiment. So remember, I've created a bunch of new samples that evade my model. Why don't I just use those samples and feed them back to my model and say, hey, look, you missed these. These are bad. And it can learn from these. Now, you have to be careful here for reasons I won't go into great detail, but in our toy experiment, we showed that by wrapping these samples, by learning from these mistakes, that now a new attack launched is no longer successful at 12%, but at 8%. So that's essentially a 50% increase in efficacy against attack by learning from your own mistakes. Okay. Okay, I've talked about how machine learning can be exploited. I want to spend a few minutes very, very briefly on how machine learning can be weaponized. And this is a different use case for adversarial AI. I just want to make you aware of it, and I won't go into great detail. So I'm going to flip through charts quickly. But let me just show you these. These are kind of interesting. So first, work we've done showed that you can use so-called generative adversarial networks, which is essentially one deep learning net competing against another one, to generate domain names that look totally real but are 100% artificial. And I'm going to skip through how this works mostly. Briefly, it's a competitive game where I insert a random seed to the red model. The red model generates a domain name that's specially crafted to bypass, like to get misclassified by the blue model. And then I teach the blue model to fix its mistake. And then I do this thing again. And through a series of rounds, two things happen. The blue model gets better at detecting fake domains, and the red model gets really good at producing fake domains. So what's interesting about this process is that the domain names generated by the red model in the end are domain. They're totally randomly generated. The input to this is a random number, and it outputs a domain name that I think to your eye and to mine look like they could be legitimate domain names. In fact, I think a few of these are registered domains, laner.com, maybe VI Etips, for example. But these are wholly artificially generated and could rise to a new kind of malware. Ransomware uses domain generation algorithms to call home. And this is what the current state of the art looks like. And to your eye, it's really easy to see that those are pseudo-randomly generated. But if you saw statpot or laner.com or something in your DNS logs, then you would maybe not jump to the conclusion that's coming from a domain generation algorithm. Interesting about this is that these not only fool humans, but they fool classifiers. Different classifier, not the deep learning it was trained against, a random forest classifier that catches most of these ransomware and other families totally whiffs on these DeepDGA algorithms, these DeepDGA names. Another offensive use case for AI comes from a colleague. I'll actually be giving an RSA talk with them, where they mined Twitter. So what they do is they read your Twitter account and they learn the conversations, the kinds of things you talk about. And from that, they can create, so those tweets are publicly available, obviously, and they can create totally artificial tweets to you that are relevant to the conversations you have. And all they do is they can show you, they can inject a malicious link at the end. So like, oh, look, here's something about Pokemon Go, and I've been talking about Pokemon Go, so I'll click this thing, and all of a sudden I'm owned. So that's really interesting research. Other offensive uses of AI. Many of you may have seen Vicarious AI published several months ago how they broke CAPTCHA. So they have trained a machine learning model to solve the CAPTCHA puzzles, so that no longer is that form of dual authentication necessarily safe against automated techniques. I want to end here just in the big picture. Offense is structurally dominant in AI, just like every other thing. And there's a few good reasons, but I want to point out that there are some things we can do to level this playing field. One thing to point out is that I want to point out this item number 3, that as a defender, we often pay more attention to protection coverage than the minute details. Whereas an attacker really only has to focus on the details and find something that you've overlooked, and that is his entrance in. This is especially true in machine learning. So we're, we overemphasize perhaps getting the right answer all the time, and underemphasize understanding how we got that answer, and that can be exploited by an attacker. Lastly, some high-level strategies against AI. I think that I mentioned one. We can attack. We can red term our own machine learning. We can use layers of defense. We can demand model inspectability, and we can begin to use more of the same techniques that attackers use by using cleverly unlabeled or cheaply or poorly labeled data. I'll end just with one humorous offensive AI for defense. If you haven't seen that, I encourage you to look it up. It's called Rescam by NetSafe. And this is if you get a phishing email from a scammer, you can forward it to them, and they will use an AI to answer back for you to keep the scammer busy. So the funny thing here is that, some email that the AI generates this test. I don't speak Russian. Is that going to be a problem? Is there some basic phrases I should know? I'm apprehensive. How do I say that in Russian? And it tries to create a conversation and tie up a scammer who may not be automated at this point. So with that, I will leave you with this slide and my predictions for AI and infosec, and stop my presentation and allow you to ask any questions through in person or on Twitter.
All right, can you hear me? All right. Hey, Dr. Anderson, thank you so much. During your presentation, I received 3 questions. Now, for the audience, if you have a question, I'd like to invite you to send your question to via Twitter to hashtag cybersecurity live. There, we'll collect your questions and forward them over here to Dr. Anderson. But so far, we've already received 3 questions. The first question I have for you, Dr. Anderson, is do similar techniques exist for dynamic malware detection?
Yeah, it's a good question. So everything we've talked about today is static malware. That is, the malware looks at bytes, or the detector looks at bytes on disk. Dynamic malware detection is, rather than look at bytes on disk, let me look at sort of the runtime artifacts of the malware. And it's a really good question. So runtime artifacts of the malware might be API, dynamic API sequence calls that the malware makes or whatnot, or network traffic. To my knowledge, that's a really hot thing in detection. To my knowledge, there's not a lot of work in evading that yet. It's a harder problem, but that would be an excellent excellent direction for future research for a lot of this.
Okay. Our second question that came in is there any evidence to suggest that attackers today use machine learning or AI in their attacks?
Yeah. So I've seen press that claims that, but my personal opinion is that there's not yet evidence to suggest that attackers are using machine learning for sort of infiltrating networks and endpoints. I believe there is evidence to suggest that people are using data science for, phishing, identifying targets, crafting emails. If AI for sort of penetrating networks and defenses, I guess I'd have two questions back. Is number one, would you care if it came from AI or just automation? And number two, how would you know if you did see it? And probably you probably might be able to know recognize AI versus other automation by this trade-off that I mentioned previously. That like in reinforcement learning, agents often begin by exploring the space, and then when they find an exploit, they exploit. So it's an exploration-exploitation trade-off. So would you know it? Would you know an AI attack if you saw it? Maybe, and maybe by that method.
Okay. And the third question I have, I'm going to have to kind of summarize it because it was a pretty long question. But in summary, do you think artificial intelligence will be taking infosec jobs?
Oh, yeah. It's a good question. So I didn't leave this slide up for very long, but one of my predictions is actually the opposite. Myth number 2, data scientists will replace infosec jobs. I don't think so. We have a 40K infosec per year job deficit in infosec, and that's going to only get bigger. And anecdotally, what I've seen is actually the opposite. I've seen really smart infosec people just adopt machine learning as yet another tool at their disposal. So one of the guys who does machine learning the most at my company, Endgame, is not, he doesn't have a formal degree in machine learning like I and some of my colleagues do. Instead, he's an infosec guy who's just really smart, has picked up these tools and now uses them for really clever applications. He actually kind of has a leg up on us, formally trained machine learning folks, because he knows much better than we do the application space. So I guess the short answer is I actually don't see a reduction in infosec jobs. I see infosec jobs being scaled and automated, but it'll be the infosec professional who's doing the scaling and automating, not him being automated out of a job.
All right, great. Those are great answers. Those are the only questions that I had that came in. Dr. Anderson, on behalf of University of Fairfax, again, we really appreciate you taking the time to educate us tonight. And to the audience, we appreciate your participation in taking advantage of this wealth of knowledge. And so with that, we'll conclude. Dr. Anderson, do you have any final comments?
No, thank you. Good luck to everybody out there, and I hope to see you at a future conference.
All right. Okay, thank you. All right, that concludes our broadcast for tonight. Thank you, everybody, again for participating. The time now is 9 o'clock in Eastern. All right, goodbye.